This video is on uniform circular motion. When we say circular motion, we're referring to revolutions, not a rotation. Two are different, follow different rules. So what is a revolution? A revolution means that an object is moving in a circle around an axis that is external to it, meaning that it's going around something that is outside of it. The term uniform means that the object is moving at a constant speed. Now notice I said speed, not velocity. So here's a picture of what that might look like. Suppose you have something moving in a counterclockwise circle like this. Velocity arrows are all the same size, but notice that they're changing direction. The velocity of our object is always tangent to the circle. Remember, tangent means perpendicular to the radius, touches a circle at only one point. And so that velocity is not changing in size. We can find the velocity, since the speed is constant, using our all delta x over delta t relationship. For a circle, we're going to write that like circumference over period. And the circumference of a circle can be found from 2 pi r, and then t is the symbol for period, which means the time needed to complete one revolution. So again, notice that even though the velocity arrows are staying the same size, in order to be moving in a circle, they have to be changing directions. At one point it's going to the left, and then down, and then right, and then up. So, since our velocity is changing, then we know there's an acceleration. And so we're going to end up calling that a centripetal acceleration. So again, a revolving object is accelerating because it is changing direction. So since the direction is changing, the velocity is changing. Since the velocity is changing, there is an acceleration. The acceleration is going to be directed towards the center of the circle, or directed towards the axis, if you'd like to say it like that. An adjective that we can use to describe that direction is centripetal. Centripetal literally means center-seeking, or pointing towards the center. The acceleration, therefore, is perpendicular to the velocity, so the object doesn't speed up or slow down, it's only there to change the direction. So again, because the velocity is changing direction, we have an acceleration. That acceleration is directed towards the center of the circle. So kind of looking at our same diagram again, there's our velocity arrows. That's what the acceleration arrows would look like. Always directed towards the center of the circle. If it wasn't directed towards the center, then the object will be speeding up or slowing down or moving some other path. An equation that we can use to find a centripetal acceleration is v squared over r, where r is the radius of the circle. Of course, if we're going to have an acceleration, that means that we need to have a force somehow, some way. So remember Newton's second law. To accelerate an object means we have to have an unbalanced force in the direction of the acceleration. That would be our net force equals ma equation. And so in order to make something turn, we have to have a force directed towards the center of the circle, or towards the axis if you like. Again, we can use that adjective centripetal to describe such a force. But the word centripetal, remember, is an adjective. It's not actually a new kind of force, it's just a word that describes forces that we already know about. So we don't have any new forces. Here they're just doing something that's different. Here that the word centripetal just means that any force is directed towards the center of the circle. So for example, suppose you have a ball on a string that you swing in a circle. Since it's on a string, then the force that's exerted on it would be a tension force. And so since tension is making it turn, tension is centripetal. In a lot of problems, the first step is going to be to realize what force is acting as a centripetal force. Another example, car turning on a corner, something that we do all the time. The force that keeps the car in contact with the road, keeps it from going in a straight line, would be friction. So in this case, friction is centripetal. It's making the car turn. Another example, the moon revolves around the Earth, if you didn't already know that. The force keeping the moon in orbit around the Earth is gravity, and therefore gravity is centripetal. And so any force can be a centripetal force if it's causing something to turn, and when you have something that's turning, you need to identify what the centripetal force is. We can use Newton's second law to figure out the size of a centripetal force, just mass times acceleration. Since our acceleration is centripetal, we'll just write it like mass times centripetal acceleration. Substituting in our expression for centripetal acceleration, we could write that like mv squared over r. And so in a lot of problems, we'll be setting a force equal to the quantity mv squared over r. So, simple example. Suppose we got a 500 kilogram car traveling north at 20 meters per second, and it makes the left-hand turn, which means it's turning to the west. We want to figure out the frictional force between the car and the road. We're going to assume that the radius of this turn is 400 meters. So it's a pretty wide turn for a car. To draw a simple picture, here's our car going north. It's going to make a left-hand turn, so it's going to go like that direction, meaning that the frictional force acting on the car has to be to the left or to the west. And so by drawing a diagram, we can figure out the direction of the force. To figure out the size of the force, we're going to need to set the frictional force equal to the centripetal force, meaning I can set it equal to mv squared over r. This is what we have to realize, is that since the frictional force is centripetal, we can set it equal to mv squared over r. And so substituting in our numbers, we would find that the frictional force is 500 newtons. And then to give a complete answer, we need to say it's 500 newtons to the west. Now that last example was relatively simple. The next couple examples we're going to look at are vertical circles. If something's moving in a vertical circle, then that means that it's got two forces acting on it possibly towards the center. We have to include gravity, in other words. So suppose we took our ball on a string example and we turned it so that it's going vertically. Picture might look like this. We have to remember that gravity always acts downward. Now at the top of the circle, tension will also be downward. The center of the circle is downward from the top. And so the centripetal force would be tension plus gravity. At the top, gravity is helping it turn in a circle. At the bottom, tension will be directed upward, and it's going to be much larger. And our centripetal force would be tension minus gravity. So at the bottom of the circle, the tension in the string has to do both the job of holding it up and turning it in a circle. Gravity is trying to pull it out of the circle. So, to kind of put some numbers with that, suppose that the ball had a mass of 0.5 kilograms and the string was a meter long, meaning the radius of the circle is a meter long. And suppose we swung it at a velocity of 4 meters per second. We want to figure out the tension in the string at both the top and the bottom. Now the tension is not a centripetal force. It's part of the centripetal force, but we also have to include gravity. So if we just calculate the quantity mv squared over r, and we get 8 newtons, we have to realize this is not the the tension. This is the sum, vector sum, of tension and gravity. So at the top of the circle, that 8 newtons is equal to tension plus gravity. So putting in numbers like that, we can see that if we subtract the 5 newtons from both sides, the tension has to be 3 newtons. At the bottom of the circle, that plus sign, it becomes a minus sign. And so the 8 newtons that we got from mv squared over r is equal to t minus 5 newtons. So at the bottom of the circle, the tension has to be 13 newtons. And so don't always be in a hurry just to set one force equal to mv squared over r. In some situations, most likely a vertical circle like that one, we have two forces. So we need to draw a free body diagram, kind of like we've always done, something like that, to determine what two forces, or possibly even more forces, are the centripetal force, and then use that to figure out how big our given force is. This is the end of our lesson on uniform circular motion.